these diagrams illustrate relative measures of describing and absolute measures describing historical locations in time and distance. And what we have is an eye of God perspective looking down at some point in T1, and here it is at T2 where the distance between the 2 points has expanded. And initially what we do is we place a series of light clocks. Let's say it takes 1 year for light to go from one end of this light clock to the other. So it's a series of 8 light clocks as seen from an eye of God perspective at T1. And then as time goes by, from the eye of God perspective, we can see that all the relative measures of light clocks have all proportionally expanded. But it's only from this eye of God perspective that it would be seen that this relative measure of time has lengthened. So when the photon finally arrives, it arrives after 8 light years have passed. Each light clock is still 1 light year long in relative measures. From the absolute perspective, you can see that it's going, there's been a change. Now, what this means is from a relative perspective, if we look at it over here, when a local observer looks back in the past, there was a series of 8 light clocks. They were smaller in the past when the first light came out, and they incrementally have increased their measure of length, but they've proportionally maintained that 8 light year. So the local observer sees the eye of God interval of time as it was seen or established in the past. You are seeing the actual historical location of the object in absolute measures of where it is in time. So now there's one little relationship that this is kind of handy to have, is that what I call the look back time or look back distance, since time and distance are interchangeable, that if we are observing here, this look back distance is defined by this, and this is to a certain point in historically in measures of time, and you have TO, the age of the universe. So we can write the ratio of time is equal to the age of the universe minus look back time divided by TO, the age of the universe. So that's a handy relationship. Now, that will be used later on in some more fundamental relationships. Now there's a real problem with this model as presented so far, is that there is really no expansion. Let's say, for example, let's take these little circles here represent galaxies, and here is a matrix-like relationship in space and time, and every galaxy is defined at some point in space. And we go back in time, and we would see that this matrix-like relationship has kept their geometrical location in time. There is no change. They are keeping their fixed relationships. The universe is perfectly flat, and they're keeping everything is square, but there is no way to measure an expansion rate or variation. And this is a problem because when we look at the real expansion universe, we see that there is change. The galaxies really have a velocity. They really are moving or appear to be, being carried by expansion rate at a rate that the velocity of expansion, for example, should be greater in the past, and we see it slowing to our present rate that we see, obviously. But this model, there is no expansion. Nothing is changing. So almost in a way, the model is too good. And now another problem with the model as presented so far is that there is no cosmological time dilation. And I should explain this a little bit. What is time dilation? Well, let's say we're at a bowling alley and we throw first one ball, and 1 second later we throw another ball at the same speed, so with a 1 second interval between. Now when the balls hit the far side of the wall, there will be a 1 second delay between the first and the second ball hitting the wall. But now let's say we throw the balls down an alley, and the alley is expanding. Well, and the balls maintain contact with the structure of the expanding bowling alley. Well, now when they're expanded, the distance between these two are going to be increased because the space between them is stretching. So now when the bowling balls hit the far side, it's going to be a longer interval of time than when in a non-expanding bowling alley. So this dilation of intervals of time, a past interval of time and event, it becomes dilated when observed if something is expanding. Well, this process of time dilation is observed, okay, except for in quasars, which is very mildly observed. But for example, if we consider type 1a supernovas, they have a light curve that goes up and then comes back down. And depending on where you pick the dimness, the cutoff point, roughly it takes 20 days for the light to go up and down. And if we were to look at a type 1a supernova with a redshift ratio that was 2, that it would be, or Z1, instead of being 20 days, it would now be 40 days. The period of time has been dilated associated with this, how long the event it would be observed. Well, the problem with this is that with the PROS model, there is no time dilation observed. For example, the faster clock rates, if we were, let's say, look at a pendulum in the past and we would see it ticking faster, in the past it would be ticking faster. Well, they should say, well, we should be able to see this faster clock rate. Well, when you go through the relationships, sure, the clock rate was faster, but as that information is traveling through expanding space-time field, that interval of time defined by it is being dilated by the expansion of space, and dilation happens to be exactly inversely proportional to the faster clock rates predicted in the past. So this is another problem for the model. Time dilation is observed, but this model negates it. In fact, everything is being kind of eliminated out of it. So these have to be addressed it indicates that the model as presented so far is incomplete. This talks about the first equation, how I got it. We don't need to go through that. And okay, maybe a summary of some of the predictions. The summary: geometrically based relationships were derived that predict the response or actions of an object within an expanding space-time field. It's kind of geometry. It's amazingly dynamic, but like a diamond has a geometric shape, so does the behavior of objects within an expanding space-time field. The accelerative field associated with gravity and Coulomb's force was predicted properties of an expanding space-time field, which also corresponded to inertial forces like linear and circular acceleration. Relative measures of intervals of distance and time were preserved or invariant with the passage of time. Absolute measures of time provide a means to describe how local clocks slow with the passage of time. And 2 dimensions of time were being described. I didn't make too much of a point about that, but I guess it kind of became clear as I was using relative and absolute measures of time. They are geometrically related, but they are definitely unique. The effect of gravity and charge was predicted to decrease with the passage of time based on absolute or global measures. And while there is no evidence of clock rate variation directly, cumulative measures of time should be observable. And the proposed expansion includes the space within the atom itself. Okay. Now, there are at least 4 fundamental issues with the problem so far. A traveling photon does not lose energy at the same rate as other field-based relationships or matter. The equivalence between matter and energy is not preserved, which existed in the present model, limited expansion model. The cosmological redshift is not observable, or there is an ambiguity with respect to the energy of the photon over the time. The cosmological time dilation is no longer observable, and the distance and temporal intervals separating galaxies would be locally observed to remain the same over time. The densities over galaxies would remain the same. There would be no expanding universe. It's kind of amazingly ironic that that expansion is eliminated from the model itself. So now that kind of concludes. Here's a basic list of some of the formulas there and the graph representing it. That concludes the development of the model with respect to expanding observable space, and you can see there are some shortcomings in the model so far. So the model as presented is incomplete. It's interesting, predicts some fascinating structure, but it's incomplete. Thank you so much for your time, and on to the expansion relationship associated with unobserved space.